Okay. Okay, let's start. Okay, maybe problem one. We can split between a couple of people. Maybe let's see how fast it will go. Окей, можно я вас попрошу тогда первую часть первой, а потом посмотрим.
Okay, the problem we are given agreement manifold. Which with the connection. Tensor defines the following way. Okay, first we want to prove the following equation for arbitrary vector fields. Okay, let's rewrite it by the definition.
So you don't need U for now, right?
Sorry?
You don't need four vector fields. Just
Yeah.
So okay.
Probably.
No. Yeah.
It's even just on the head, not for the first, but for the following, it will be a bit more vector fields. Okay. I've related by summons. First summon. Second summon. We want to regroup it the following way. We will have, for example, from this summon and this summon, we will take number web, and for others the same. We will have three summons like for example, for this, like
we need to use torsion.
Yes, and I said that Levy-Chivit connection has no torsion. We proved it somewhere previously in our list, and I will group it into this one.
Terms, yeah, which.
Yes, this one like this. And finally, I will come to Jacobi identity.
Okay, let's see.
Because it's too small. And three red summons. This one. Okay, as I said before, Levy-Chivit connection has no torsion. That's why we replace this set bracket, this one, set bracket, and this one. Okay, and finally we once more apply that Levy-Chivit has no torsion. It will group again this one with this one, with yes, no, with this one, and the last one with the rest. And we'll have the following. And it's Jacobi identity, and from previous lections and seminar we somehow proved it as well. We know that it's equal to 0. Like this.
So for example, this one where you have commutator, you pair with which one to get to apply it?
Which one?
So the first commutator W. So you have nabla of so the first line.
This one will be this one paired.
So it's not
Because this vector field is here and this vector field is here.
Okay.
Yeah. This one will be paired with this one, and this one with the rest.
Okay.
Yeah, like this.
Alright. Okay, so maybe it was fast enough, so maybe you can do the second one.
Okay. Disconnect. Okay, as I said before, we took arbitrary four fields. That's why I will not write them again. We want to prove the following equation: skew symmetry. We had the hint to look for a case when z is equal to u, and we will do it. But firstly, I want to notice that our R is skew symmetric. That means that this one is equal to this one. Just to notice and remember it. Okay, just by hint. That was given. Let us write down everything again by the definition. Okay. our remaining metric, and like all matrix is linear, we can just group it in different summaries. Okay, let us first look on two first summaries. We want to prove that they actually are equal to go to zero because все запрещается, короче. Let us take okay, let us rewrite it. It will be the following. The first one. And the second one.
So you can write it because
Actually, because we did like that on lectures previously.
yes. So so this is because it's Hibicivita, right?
Yeah.
And basically from the fact that it is invariant. So this basically means from just direct application of the fact that G is number invariant.
Yeah.
Because
Just I consider it like property. Just do it.
so we have this, right? Which is the same as a number V applied to G W Z is the same. V applied to this function is the same as G number V W Z plus G. So
And number
basically,
is like-
Leibniz rule works.
Now was a second.
Yes, W. So this is actually the same thing. And so that's what this is.
Yes, these two summaries are the first one, and the bracket is the second one. I will write it finally. Now I just rewrite this one and this one. Because I will, by this very rule, take again number out, and they will.
We cancelled.
Yeah, cancel. Thank you. Okay. Actually, there are. I can write the following. I cannot explain, but it's a lot of calculations. If it's needed, I will explain. Just to tell how we get the following, we by that rule take nabla again outside, but we will have summons where nabla is on the second position, but by symmetry of G we can just replace them and put on the left side of our equation, and we will have 2 of this one equal to actually this. That's why such constants appear. Don't need to write it down. Okay. And it's clear they cancel, I guess.
Do
Okay, I also used the fact that
they? So maybe you took some special.
yes, I took some special vectors. In the general case, I need to say something about this cancel with this, but it's a bit with this one, but it's a bit difficult. And I remember the fact that to prove 2 tenders with the same signature are equal, we need to check our equation with assumption that our Lie bracket on taken vector fields, vector spaces, vanishes. I do understand it like our G is just something from yes, and when our Lie bracket vanishes, it's just basis 1, and if we check for basis, we check for everything.
Well, you can fix first a point, and then this point doesn't really matter which vector fields you take, as long as you like if you fix values of a vector fields at this point, doesn't really matter what is going outside. So if you prove for any. Well, you can prove for any, proving for this special. But actually, this is easy to see that this bottom thing is the same as G of number of commutator of Z.
No, it probably isn't because of this equation.
Yeah, exactly.
It
Yes.
isn't because
No. So this is exactly 1/2 applying the commutator.
but the commutator should also get into the second element.
But the
Yes,
G
it
is
is.
symmetric, and you have 1/2 here.
Which is
So that's the whole thing. Yeah, so it's not.
And we can say
it's-
like this, by that variable.
Yeah, so this equals to a 1/2 of what's written.
Yes, because we will put nabla out, it will appear in the second, we will put it on the left side, have 2 of this one equal, actually, to...
No, so you apply commutator to G of CZ. That's what you do.
Do I need to write it?
Yeah, sure. Yes, so you apply commutator, 1/2 of commutator, actually. Right?
I will use symmetry. Here. It's this summit will go here. We will have like this, and like this. Wait. Sorry. And this is what we have here.
Okay.
Last one.
Okay, maybe for the third one, let us torture somebody else. Thank you. People who want to torture. Somebody with just number one. Okay, maybe G-Ping? Yeah, so part 3 of the first problem.
I need to draw the part 3 or
Part 3.
Oh, okay. So our goal is to prove this. So first, we write this guy to by the first property we have proved we can get one by the first property of this guy, so you can equivalent to two terms. Then use the two property. We can exchange this part and minus this positive, so we can get and then we use the first property again. We also decompose this two parts.
So each term now becomes sum of 2, right?
Yeah. Okay. So you will get 4 parts. Minus G. This is the decomposition of this part. Minus G. We use W. then we use also again the second part, the second property you have to prove, and plus a very trivial fact. You just
Percentage symmetric, yeah, and it's
Yeah,
just
yeah.
two images.
yeah, you will get a minus. No. So you will get you apply this. You will get G. This is this part. G. Maybe we just need this condition, and we will this condition later. So these are things, so we get two. Plus G. So we continue to compute this part.
Okay, so what happened? You pair these two, and so the U, VW, so these are the state.
Yeah.
Two.
Yeah.
This and then the other two left. Okay.
This is just we add together. G. And this we can apply the fourth property again. Since the fourth property are three sum, so you can get a minus. Okay. Minus 3. since this is the guy we want to get here, and if we can, we want to just put this minus part to this side. If this is the same as this, we will prove this property.
Well,
So-
it is because of WB.
Yeah.
It is
Yeah,
because
yeah,
you
yeah.
get 2 minus.
Yeah. This is since you first take change, so you get you,
Yes.
and then we apply this property.
Yes.
So we this property here. Yeah, you just exchange with W. This is the minus. So then this guy is same to this. So you just put it in the left side, so you get the point.
Okay.
Don't forget that not the minus changes to the plus, and the arguments inside the R also change. So you get 3 times G tap of 3 metrics, not 1 metric.
No, this guy goes to the left, you will get 2 of those equals to 2 of those. Then you divide both sides by 2, you get a solution.
Yeah.
Okay, so let's go number 2. Number 2. Who was not? Everybody. Okay, Mikhail, maybe you can
So we need to prove that metric is Einstein if and only if for fixed dimension of manifold 2. Then we need to prove that Ricci tensor equals lambda G. If and only if is constant. So in the site this, it is trivial. We just remember the definition of RFP. Actually, we need some orthonormal basis, but the answer doesn't depend on the choice. So we fix some E1, E2 for normal basis in okay. So just by the definition, definition is sum of.
Sorry, which answer does not depend on the basis?
I mean theorem.
Okay.
The definition depends on basis,
Yes, okay. Yeah.
but the statement doesn't depend. So just by the definition, it is Ricci tensor. But we know that Ricci tensor is just lambda times j, and we know that because just by the definition of orthonormal basis, it is true. So just lambda times. And it is constant because lambda is constant. Yes.
Okay, let me see what happened. So your EI is your orthonormal basis. You take Ricci. So lambda. This is just you use this.
The easy side.
This is just 2 lambda, and you get that R is just dimension times lambda. This is always like that. By the way, if it's Einstein, then the section, then the scalar curvature is n times lambda. So
But
in this case,
fixed
it's
dimension.
Yes. Okay.
So it was the easy side. Now we go the other way. So we have that R doesn't depend on a point, it is constant. So we need actually to fix this basis in each point, to define Ricci tensor and R of P. So this choice is fixed. Now let's just write by the definition of R of P using the using the results from the problem 1. By this symbol I write J of, so it's just this form.
So just form given.
This is the first sum. Now we write the second one. Let's just denote Rm of QV WZ. This for simplicity. WZ. From the first task, we know that it is for example, this is 0 if the first two arguments are the same. And 0. It's just because it's antisymmetric. So we have that this is 0, this is 0, and we actually can swap these pairs. Equals and we see that if we swap, we get the same element, 2 or m of miscellaneous. Okay, it was a calculation of RP. Now we need to calculate Ricci tensor. So let's calculate Ricci tensor not only in with these arguments, but because it's symmetric, it's enough to only write this. So by the definition, it is also will be 0. So it is we can, so this is 0 and this is 0. So cross term is 0. And we actually know that Ricci tensor, so we just calculated it already at E1, E1 and E2, E2. Is the same, and it's just Rm 1, 2 to 1. 1, 2, 2, 1. And due to this calculation, we know that it's just 1/2 of
Section of scalar couch.
which is just 1/2 of R at point P. So we also know that J of EY EJ is delta by the definition. What we know about Ricci? So we know that cross term is 0 and diagonal term is this constant, so it's 1/2 RP delta IJ. And it is half RP IJ. We prove the statement in some basis, actually in orthonormal one, but it is true in any basis because Ricci is so-called tensor. So if we do change of coordinates, Ricci and J just behave the same way. So if So it's true for any so-called tensor equations. If it's true in some basis, then it's true in any basis. So we actually find some basis in which it is true. So then it holds always.
Okay. Yeah, just to comment that this was called, I think, if I learned that not very good way. Well, I kind of didn't. I forgot a lot of things, but I think this is like a lambda term in Einstein's equation. So actually, if it's zero, right, and there is no like a matter, then the curvature is zero, right, and you have flat geometry. If you have some matter, then it gives you like some additional tensor, and your curvature becomes not zero. So you
Scalar.
like well, Ricci curvature. So Einstein's equation is equation for Ricci curvature. But if your lambda is not zero, it's like what's called lambda term, and actually responsible for, if I remember this correctly, whether our universe collapses at the end or not. Because like for some, so you have like a compact space-time, so it collapses at the end, or like a non-compact, so it expands. So something like this. Yeah. And also, do people know about pizza problem? Pizza problem. So actually, yeah, thank you very much. This is just something. No, I learned that when I was a graduate student, and I think this something just fine. So actually, in two-dimensional case, scalar curvature is the same as. So there are different names like sectional curvature, also like Gaussian curvature. So this is all the same. And actually, in this case, it just equals to the product of eigenvalues of Ricci tensor. I don't know, maybe times something, maybe sometimes some constant depending on 2, but I don't, yeah. So you have like K1 and K2, so these are eigenvalues of this. Well, this guy is symmetric, so you can diagonalize it, right, you can find eigenvalues. And these was called principal curvature. So you actually have principal directions, which are eigenvectors of Ricci. And so you compute, like, you invert the radius of a curve. So curve locally is like a circle. You invert the radius of the circle. This will be, don't even invert, just the radius of the circle is the curvature. No, I think the smaller radius, the biggest curvature. So invert. Yes. And so, anyways, pizza and Gauss proved that sectional curvature is constant under isometries. And this actually tells you how you should hold your pizza. Because if you have a pizza slice, there's a big problem that it curves this direction. It's very hard to beat. But if you hold it this way, then it becomes straight this way, and you can eat it. So this is just because it's isometry, and you had like a constant curvature here, should go to constant curvature in this direction. And so, well, if you don't tear it, right, that should be in isometry, and so therefore Gauss actually told us how to eat pizza properly. Anyways.
Okay, let's do. So, okay, people. There's only one person who did something other than 1 and 2. Nikolai. We use you. So what do you want more? Fourth or fifth?
I guess fourth.
Okay. And I'll comment something why I put fifth problem because well, something that I couldn't finish myself, so maybe you can finish. That's first.
Okay, the fourth task was to do the same thing as in the problem 3.
Yeah, we didn't do 3, but actually
No?
just this is just you have metric on hyperboloid, and so you need to compute components of curvature tensor, Ricci curvature tensor, and sectional curvature. And here this is actually Einstein.
Okay, we have a hyperboloid of radius and quotes r, yeah, which is as a sphere
It's
seen
a
as a
sphere of radius minus r. Right?
imaginary sphere. Okay, well, with the property that I try and avoid that. Here's t,
Okay.
t squared minus well, and t is greater than 0. Well, we have metric G on HR that is I'll pull back over the Lorentzian metric on Rn plus 1. Well, H, where H is this guy. Okay. Okay, so the task was exactly first to compute our ADKL. Second, Ricci curvature tensor and the scalar curvature. And or to show that this equation holds for some lambda. Yeah. Okay, we can pick a point on HR, well, and take the orthonormal frame, orthonormal basis, and exactly at point P in TP HR, well, the in the tangent space. Yep. And this choice of particularly orthonormal frame gives us the very useful identity from orthonormality. Well, it is orthonormality itself. Okay. Then I would like to use the result that relates R ijkl with so knowing that HR is the space of constant curvature, of constant sectional curvature, I know that, well, I don't know exactly if we can use Ricci decomposition here, but it implies that we have this. So,
This, say it again, this holds well. What should be true for
our space
for G, so that this is
must be the space of constant sectional curvature.
but why do you know that it is constant?
Well, we could, I guess, use the fact that with this metric, hyperboloid is isometric to, is locally isometric to hyperbolic space with in Kleiman model.
Locally symmetric to
Isometric.
I'm not sure that I understand this. What does it mean? Well, you can use symmetry though. You can use symmetry with respect to the observed orthogonal group. Actually, right? With so a group that leaves the metric invariant of the signature one and so on. Then indeed your curvature should be constant.
Yes.
But okay, this should be some check, but still.
Curvature, not sectional curvature.
Well, sectional. Curvature.
Sectional. Okay. Well, this no, the constancy of sectional curvature implies this for this metric, and well. Now we can use that J that is the chronic delta. Well, hence are the components of the Riemannian curvature tensor R times, well, okay, I can just do this. Okay.
And by the way, SO1n is principal SO1n minus 1 bundle over hyperboloid. Because it acts transitively on hyperboloid with,
Yeah,
stabilizer SO1n minus 1.
you mean
It's just to refer to what
it can be seen as a homogeneous space?
Yeah. Just to refer to what was to something that was studied on today's lecture.
Well, and to compute the Ricci tensor components, we need to do a contraction, but we need to write it in this way, which is RIM, if I wrote it correct. Okay. Well, and Rick IJ will be no, okay.
Yes,
Correct. Well,
seems like
we can do it here. No,
this is exactly what. Yes.
there will be opposite. I'm afraid of. No. Well, okay.
No, this
This-
I think is true.
And okay, and what is R? R is Rick contract with itself. Maybe I should.
And, yeah, by the
This
way,
is, but
yeah.
here for orthonormal basis it is true, but I guess in non-orthonormal basis there must be G or G, because we contract with the metric and not with itself.
Yeah,
just
that's
with itself.
that's what.
But we in orthonormal basis, so
Mhm.
all is correct. Well, and I can write down the answer. What we have is that. So well, R.
Well, so far it is not your left left side of what you wrote is not related to right side at all, except that Gij is delta Ij. So we need some relation with R small, right? Well, okay, that's what I guess you.
So the only one relation is this.
Yeah. So I'm just saying that so far there's no relation between left and right word except that Gij is delta ij. And maybe that R is that your curvature is constant, which you did not prove, but kind of okay.
And I have made one mistake. Here must not reach a scalar. It must be the our constant sectional curvature.
Which is the same.
Well,
Or maybe divided by 2 or something like that.
they will differ by a multiple of n times n minus 1. So,
Which is 2.
for arbitrary n, I get this, or this task code for n equals 2. No,
No. It's just,
it was a
yeah. In this case, it's not when equals to. Yeah, sorry.
It was, if it was for n equals 2, it would be less pain. So, and k for hyperboloid, it is negative 1 over r, if I'm not mistaken.
No, this was the whole point to obtain that it is. Well, actually, negative r squared. And I think just negative. Negative. So yeah, I guess 1 over r. Yes.
1 over. Well, r cannot be 0 or less. So well,
Yeah, but that was the whole point actually to.
yeah.
Yeah. Well, how do you know that? Because otherwise you just once you know that you just plug in into formulas and compute. And we don't even know, we don't even have this result that if your scalar curvature is constant, then you can write the curvature tensor like that. Well, you can easily compute it here, just from definition, and then you get exactly k, like just from your computation, you will get that Rijk is this deltas times some number that you get out of the computation.
Here is the simple logical mistake is made. Okay, well, we must do all the steps then. So Rijk L is defined as no half, yeah, just the formula.
For some reason, I wanted k to be something like negative r squared, which I don't like, because if it's curvature should be as r grows, curvature should be closer and closer to 0, right?
Yeah.
So, yeah.
So is for hyperboloid, but from the negative side. Okay. We have. Okay. Let's start over. So we have an orthonormal basis at point P. Well, it gives us the 3D identity So in in coordinates we can write curvature tensor. So let's do it as it is written on the problem sheet. Yeah? So Ri jk L. This is obtained with this, and we have a curvature endomorphism, yeah?
Yes.
Yeah. Okay. So yeah, and where this is by definition a well, this this and as well, should this term be equal to 0 because of this vanishing bracket?
So you can take Vi and Vj such that this bracket is 0. Yes.
Well, okay, so I'll just delete it,
Yes.
remove it, okay. So we have this and, well,
So basically your Vi is d of dxi and Vj d of dxj for some coordinates x1, x.
yeah, and
Yes. You always compare.
in every coordinate system this term will vanish, of course. Yeah. So this gives us, well, we know what V J K will be, well, can be, so V alpha is
So it's best actually to so your metric depends of course on well, of course you can fix coordinates, right? At this point it's delta ij, right? But as you move out of this point, this depends somehow on this x.
Yeah.
So let us maybe write the g, like the tensor, symmetric tensor that gives us the metric. So we are in. So actually we can choose our coordinates t and x1, xn.
Yep.
So then I have this metric which is dt squared minus dx right? And actually I can choose coordinates just x1 blah 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 xn, and the first one is expressed through this,
yeah,
right?
of course.
And so this gives you I star h actually.
Well, you said that we can explicitly.
Yeah, you can explicitly
This?
compute this. Then you can explicitly compute Christoffel, because you need Christoffel symbols to compute this, right?
Yeah.
And actually you can do it just, I mean, you don't even need everything from I star h, but just second degree terms. Because when you compute curvature, you just take derivative twice. And, well, yeah. So I guess, maybe let us just compute I star h, and then
Yeah, okay.
just
So, my bad. For this, okay. So yeah, t for some appropriate
yeah. So
xi's, yeah, we can solve for t.
yes.
Yeah, it's gonna be just like, well, so dt. One over, okay.
So this sum you can actually write as absolute value of x squared or something like this. Right?
Well, so
Yeah. Okay. Just to simplify notation.
where I have mine. Okay, so okay, let it be y.
Okay.
Well, and here we have, well, two.
Yes.
Okay.
And then so then you can plug this right there. Right, compute G. This gives you Christoffel symbols, and this gives you actually curvature. And okay, so check that. So in this case, your curvature. Yeah. So what you wrote, right? Your R I J K L is negative 1 over s r squared, and then there's deltas.
Yeah.
And for sphere, it's the same formula, but 1 over r squared.
Yeah.
It just was the goal of problems to see that scalar curvature in case of hyperboloid is this guy. Just let us state it. And in case of sphere is this guy. And so you see this non-compact case, this is like a compact case. Yeah, okay, yeah.
Compact case converges and
Yeah.
compact diverges.
Yeah. Okay. Yeah, so there are many other interesting things that I didn't have time to talk about. So problem 11.5 actually is aimed at there's some relation. You have like Laplace Beltrami operator, which is correct notion of Laplace operator in Riemannian universe. And you can actually take a Laplace operator of a logarithm of distance from some point and take limit like this distance to go to 0, and this will be actually should be scalar's curvature. So you can get scalar curvature out of Laplace Beltrami operator. It's one interesting thing. And another interesting thing, again, in dimension 2, you can compare actually the area of a circle of radius r and area of which is normal circle, like area of and then area of this circle mapped by exponential map. So you subtract one from another and divide by r squared or something like this and take limit as r goes to 0.
And this will be also be actually scalar curvature. This is harder than just a usual seminar exercise, but I think it's, since we know exponential map, you can actually compare two areas in tangent space and on your remaining manifold. And this gives you, like, of course, should give you somehow curvature if you do everything accurately. Окей.
Такое отношение оно имеет только вот именно в умерных.
Ну да.
Квази.
Ну вообще да. Ну те доказательства, которые я видел, да. Ну иногда так